much better. Okay, well, thank you for coming. I was expecting a larger crowd, but maybe they're still coming because we're starting a little bit earlier than usual. And I'm going to be talking about your meeting, but that's okay. Yeah, what I want to talk about is direct potable water reuse for Las Vegas Valley. And as Carl mentioned, I've been studying this for really the past 5 years or so on my own. I'm not going to be consulting engineering firm on my own, doing this all myself. So, with that, we're going to talk about a little introductory materials first. Then some background. I think it's important that we have background material to base what's going to come after. Then I'm going to discuss the water management plans, specifically the 300-mile pipeline going north and my direct potable water reuse alternative. Issues to consider. I'm going to discuss those issues that have been brought up to me by my colleagues as being problems, but I call them challenges, I call them opportunities, and you'll see what I mean later on. With answers to these issues, and then a summary. Okay, let's get going. I start with a premise. You know what a premise is? It's something before, as a thought. Any city, town, or water-using group of people that has a well-known forecasted severe decrease in water supply and also a severe increase in water demand, and at the same time, feasible alternative maybe to make plans for interbasin challenge, interbasin transfer of water. Does that sound familiar? Like that might apply to us here in Las Vegas Valley? Yes, it does. But I'm saying that that is a strong candidate for direct potable water reuse. I'll hope to justify that in a minute. So what is direct potable water reuse? Well, it's defined in the journal. In the Journal of Water Reuse, as the term refers to the introduction of purified water derived from municipal wastewater after extensive treatment and monitoring to assure that strict water quality requirements are met at all times directly, and that introduction of purified water is introduced directly into a municipal water supply system. Kind of, the English grammar here is there's a noun and a verb. The noun is purified water, and the verb is that it's introduced into a municipal water supply system. So this presentation will discuss those issues. A bunch of acronyms, which most of you are familiar with. Adrian, is that you? So let me retake it. All right, start. Most of you are familiar with these acronyms, so I won't even go over them, but you can look at them for me. I will point out one little peeve I have. If I can point to it. Gallons per day per capita. Most people say gallons per capita per day. And just that peeve of mine, it's flow per capita, so it's gallons per day per capita. And when you use it in a formula, you're multiplying gallons per day per capita times capita. The capitas cancel out. And when I teach operators about unit dimensional analysis, then it makes a lot more sense to use gallons per day per capita. That's in conflict with many people that talk about per capita flow. Okay, let's go to the next. Okay, I want to introduce some background material. Existing water sources for Las Vegas Valley are 3 sources. Colorado River, as most of you know. Municipal wells, which some of you might not know. And private wells, which I didn't know about until recently. But take it through the Southern Nevada water system and the BMI water system, basic management for Henderson. Municipal wells is in Las Vegas Valley Water District and in the city of North Las Vegas. And Nellis Air Force Base also has municipal type wells, not private wells, municipal type wells. And then, of course, private wells that have listed on the bottom. I'm surprised by the amount of flow that we get from private wells. It's somewhere around 20 to 23 MGD, million gallons per day, which if municipal wells is around 40 plus 23 is 63, if my math is right. When you divide 23 by 60, it's about 30% of the total wells. So, and then the total wells as part of the total coming into municipal, into Las Vegas Valley is about 40%. The other 60% is brought in from Boulder Basin. Well, no, I'm wrong. About 90% is brought in from Boulder Basin. 80% is from both municipal and private wells. Okay. Let's go to the next. I never see this. There we go. All right, here's the Boulder Basin with my handwritten drawing, which is, I apologize for it, but it's good enough to show my point here, in that water is taken from Boulder Basin and through the SNWA, Southern Nevada water system, into Las Vegas Valley, and the BMI system into City of Henderson. Meanwhile, Colorado River water goes through Boulder Basin. Some of you know that Lake Mead is really comprised of 4 basins: Boulder Basin, Virgin Basin, Drake Basin, Pierce Basin. Here's a picture of the total water system, at least Southern Nevada water system, which is, of course, the major system, in Las Vegas Valley. And you'll see that it takes water from Boulder Basin and through the Las Vegas lateral, the Pittman lateral, and other south lateral, distributes water and transmits water all over Las Vegas Valley. So the Southern Nevada water system is the wholesaler, and Las Vegas Valley Water District is a retailer, as well as the system at Henderson. Okay. I wanted to now go to a flow diagram of all the water and wastewater entities in Las Vegas Valley. This is still background material for my talk. Here I have put together a flow schematic. I call it flow schematic, but it's kind of semi-physical in that Boulder Basin is down at the southeastern end, and water is brought into the Las Vegas Valley, and then uses the water, and the water flows easterly towards Las Vegas Wash. And so it's kind of convenient. We always read from left to right, and that's the situation here in Las Vegas Valley, where north is up and you can read east to west or left to right, west to east. Any questions about this? Oh, yes. I also show inside and outside use for each entity. Inside, outside, inside, outside, inside, outside. And this is important because later on we're going to talk about the amount of water that is used inside, which becomes, of course, the wastewater that's going to the wastewater treatment plants. Inside use. All the other flow that is used by all the water users in Las Vegas Valley is outside use. Now, inside use is measured very well at wastewater treatment plants. Adrian, would you say plus or minus 2% your accuracy of coming in? We used to have at the county partial flow. Now we have magnetic flow meters. Do you have magnetic flow meters?
Yes.
Yeah. The partial fluids are plus or minus 5%. The magnetic flow meters are plus or minus 2%. So it's a lot more accurate. So the inside use that we show here is relatively accurate. When you subtract the inside use then from the incoming, we know what the outside use is then just by subtraction. Inside use right now, does anybody have an idea what percent is inside and what percent is outside? Right, last year the average was 43% inside, 57% outside. An interesting side note to this is that we here in the desert use more water outside than, say, Seattle or Portland, where it's about 60 to 65%. Here, or it's even, no, it's less, I'm sorry. It's less because you have rainfall and less need to irrigate, landscape irrigation. So we here in the desert is reverse. We are using about 43% right now inside use and 57% outside, whereas Seattle and Portland are about 65% going to the treatment plants. Okay, so you get an idea of the whole valley here, the water picture. Water, potable water, wastewater, discharge to Las Vegas Wash, and then back to Boulder Basin. Okay, I'll talk about that cycle here in a little bit and how it affects the quality of the water that we drink. All right, I mentioned that SNWA or SNWS, the Southern Nevada Water System, physically, is about 90% of our potable water system. That means that the other 10 or 12% is from municipal wells, private wells, and the BMI system. And if you add these up, maybe 12 and 23 and 35, you get about, MGD-wise, is about 60 some MGD out of the 400 total that is brought in by SNWS. So you can see the proportions here. So, as I said, SNWS is blue line here. Total is green, and I'm going from 2000 to 2050 with flow on the vertical scale. The difference is about, let's see if we can find a grid line where it's processed. Oh, there's one. You can see it's about 60 or 70 MGD difference. That refers to that past slide that I just showed you, where it's BMI and municipal wells and private wells. Okay, so it adds up. Let's go to the next one. Per capita flow, as I mentioned, per capita flow, gallons per day per capita, is taking a big dive here, as you can see in here, but it has already taken a big dive with Pat Mulroy's work on conservation on outside use water and conservation on inside use, but mostly on outside use. Golf courses and landscape irrigation, change over to xeriscape landscaping. This has had a big effect, and that's why this dip in here from 1998 or so to the present. And SNWA is also projecting this decline to about, at this point here, I don't know if you can see this line right here, but that's level 1, which is defined as 1,075 above sea level, water level in Lake Mead. When we get down to that that point, SNWA is saying that that would be a trigger point to start thinking about this 300-mile north pipeline, and also triggers the shortage declaration by the Department of Interior. The other thing to point out here is that SNWA says that by the year 2035, we ought to be down to about 200 gallons per gallon per day, per capita. And I think that's going to show up on a slide that's coming up. But this is not per capita, this is making water. Conventional reuse, and I use the word conventional because I want to confuse that with direct potable water reuse or indirect potable water reuse. So it's conventional reuse, which is landscape irrigation and cooling tower makeup water and beautification of highway and Henderson, right? And maybe to a cemetery and Henderson. Yeah, okay. So that's conventional reuse. And it is taken from tertiary effluent. Now, I haven't explained what tertiary effluent is, but I think most of you know, or some of you know, that at the wastewater treatment plant, I still use the word we because I used to work there. I apologize. We use primary treatment, secondary treatment, and tertiary treatment. I'm not going to explain all of what's involved, but tertiary treatment is fairly high quality treatment of wastewater. And we have here in Las Vegas, and I'm not just talking about the county plant, but the City of Las Vegas plant, the North Las Vegas City plant, and the City of Henderson plant, combined, the tertiary effluent is one of the best in the nation. Why? Because we're trying to protect water in Lake Mead from phosphorus and nitrogen for nutrient removal. So this is conventional reuse that's diverted from the tertiary effluent from the treatment plants. And some years ago, back about 2000 or 2001, maybe some of you are familiar with a study that's called an area-wide reuse study. Maybe you're probably familiar with it. It's called area-wide reuse study. It studied the entire Las Vegas Valley, and it predicted or tried to project that conventional reuse would be up at about 50. Let's see, this is NGD, right? So 50 is up here someplace. By the year 2050, it would be around 50 NGD. Well, how come it's so different now? Well, that's because it's an older report, and a lot of things have happened 12 years ago since then. And we are now, with water conservation measures out at the golf courses and in general landscape irrigation, it's caused this dip in here. But I'm predicting that it will still climb somewhat, and that we might get up to about 25 MGD. Now, what's this got to do with direct potable water reuse and light talk? Well, if we take off tertiary effluent, then this takes off from tertiary effluent flow that I could use for reverse osmosis treatment that I'm going to explain later on for direct potable water reuse. Okay, let's go to the next slide. Okay, this is just the wastewater system. And you can see City of North Las Vegas, and they're lined up more or less physically as they are out there in Las Vegas Valley. With the 4 treatment plants, they all discharge to Las Vegas Valley and the Lower Basin. Okay, that's old news for many people. What's interesting is to look at, first of all, the inside use of water on this scale here. The inside use is the total of all the wastewater incoming and outgoing from the treatment plants, the wastewater treatment plants. It's right now at about 180. There's nobody here from the county plant to verify it right Adrian, at Henderson, you're at about 16. Where are you discharging to the wash?
I knew that was coming up. It's about 175 total. It gives out.
175 is related to this?
Mm-hmm.
Yeah, that's about right here for us here, 175. But then I'm predicting that with growth in Las Vegas Valley, it's going to do that for wastewater flow. We're going to get up to 430 MPD in the year 2050. But remember that ratio I was talking about of inside use of water related to the total water brought into the valley, being around 43% right now? Well, here we are at a ratio, I'm a little bit off. Yeah, no, 43 would be right about there, and here we are 2012. Yeah, and that ratio is going to increase. Why? Because the outside ratio is going to decrease with more water conservation and less landscape irrigation, and as people switch over to xeriscape landscaping. So when the percent has to add up to 100%, right? So if the decrease in outside use percentage goes down, that means the increase that the inside water ratio will increase. And that's exactly what happens here. That's why that increases up to the ratio up to almost 50%. Yeah, 47. By the year 2050. So that's something to look forward to. Okay, next slide is the water cycle, a total water cycle in Las Vegas Valley. Water basin, you remember, brings in water to all the water users in Las Vegas Valley. There's an outside use, inside use, and you need to label it because it's obvious. It's to the wastewater treatment plants. The tertiary effluent is used by reuse, and then the rest is discharged in the Las Vegas wash. Now this is a very simplified schematic drawing. I don't even show leakage out of the transmission distribution lines. I don't show the evaporation that's occurring and the urban runoff that goes to Las Vegas wash, the seepage, and the same thing for reuse. We'll have seepage and evaporation. There's phreatified use in Las Vegas wash. I don't show all those things. I'm just trying to show a very simple schematic of the water cycle in Las Vegas Valley. Next slide. I think I skipped the slide here. Water cycle. Oh, that's an animated. Okay. They're going to show I'm going to label here. This is the urban runoff. This is the seepage to Las Vegas wash, and this is water remaining that has to go down into the lower aquifer. Let's continue, and you will see that the labels will appear, and that's the water lost to the lower aquifer. It's amazing to know how much this is here, because if you take that 57% of this total water, that's up around 180 MGD, and you subtract, no, it's around 200 and something. Sorry about that. Then the remaining here, lost to groundwater, is around 150 MGD. That was a big discovery for me and for the university when we studied this together. Okay, next. Is there any questions about this? Can you see that I have added also the evaporation of phreatified use? You know what phreatophytes are? They're the vegetation that have long roots that reach down to the water table. And therefore, they evapotranspirate and add to the evaporation out of the system. So I should mention at this point that I've done a water mass balance. How are we doing on time, Carl?
I got 12:27.
I think we're okay. So I can explain this a little bit. I've done a water mass balance of this entire system. And there's many water paths, some that are not even shown here, that have to be calculated 6 pages for the first spreadsheet. And then when I got into a water mass balance using the Groundwater Development Project, which is a 300-mile pipeline up to the north of counties to get rural water down to Las Vegas Valley. When I did that water mass balance, that was also 6 pages of spreadsheet. But when I did it for direct potable water reuse, which is going to take longer from here, and really complicates my schematic diagram, it took 12 pages of water mass balance. I was going to bring it, but I didn't bring it today. Okay, let's proceed. Here's per capita use that I talked about previously. And you can see way back in the 1990s, we were up around the 300 gallons per day per capita. And with the efforts by SNWA Water Authority and Las Vegas Valley Water District on conservation, they've reduced this quite a ways, down to around 230 gallons per day per capita recently, and now projected in the year 2035 down to 200, as I mentioned before. 200 gallons per day per capita. Let's proceed. Oh, you know, before I show that, and before you start concentrating on that slide, I want to say some things first. One of the challenges that I hear when I talk about direct potable water reuse system for Las Vegas Valley is that one is going to cost too much, two is going to impact the return flow credits because, you know, reverse osmosis has all this brine flow which leaves the system. And then three, public perception. Those three issues I'm going to talk about in just a minute. But anyway, back to return flow credits. It's not just return flow credits. If we proceed to think about it a little further, return flow credits is what Las Vegas Valley receives as an added to their official allotment. But that official allotment, as some of you might know, is 300,000 acre-feet per year. That's out of 15 million acre-feet per year that the lower basin, California, Arizona, Nevada, and Mexico is allotted, plus 1.5 for Mexico. Million acre-feet per year. We only get 0.3 million acre-feet per year, which is exactly 2% of the total. That was thought of in 1922 with the 1922 compact that went into effect in 1926. So, the next slide I'm going to show you. Here in Las Vegas Valley. That's for the state of Nevada. So, non-Las Vegas Valley, Laughlin, Nelson Landing, some other tribal units and other minor, all take from the Colorado River, and it's part of the state of Nevada allotment. So the unofficial allotment for Las Vegas Valley is somewhere around 285,000 acre-feet per year. Subtract 15,000. So that 285,000 acre-feet per year is what Las Vegas Valley can consume or use that they call consumptive use. Some of you might have heard of this. But if we add that return flow credit to our consumptive use, and we get X MGD or million acre-feet per year, and then compare that to the actual, then we're either over or under that allotment. So now, let's see, over or under the unofficial allotment for Las Vegas Valley, now we're getting down to brass tacks. I've listed no action, meaning no pipeline going north, no direct potable water reuse alternative, just a no action over the years from 2020 to 2050. And I started in 2020 because that's when the impacts of one of these alternatives would come into play. You can see that we're still below, we're under the allotment for several years yet. I was surprised to see this, but that's because of return flow credits and the things I mentioned to you before. No action. Oh, also, since this is the zero line, I should have made that a thick, heavy line. Since anything under that is good, anything over that is bad, then you can see we're in bad trouble here after about year 2025 in that area. And the difference between direct potable water reuse, which is the blue line, and the groundwater development project, which is the green line, is about 20 mgd. So it's not that much. And that's looking vertically. Horizontally, years-wise, it's about a difference of about 5 years that you would, that the given over allocation relates to between the two alternatives. So I think that's very interesting to look at. The over or under allotment, unofficial allotment of Las Vegas Valley. Okay, here's the groundwater development project. The 300 mile is really 286, but if you add the laterals, it's roughly 300 miles. The pipeline from Las Vegas up to White Pine County with these various valleys here. Dry Lake Valley, Delamar Valley, and Spring Valley, and Snake Valley, which is highly controversial because it involves the state of Utah, and they have not agreed to this at all. So that's the groundwater development project. Can you all read that there? That's the groundwater development project. My project, I shouldn't say mine, the direct potable water reuse project would take tertiary effluent into an RO treatment facility. There would be brine that would go to a brine concentrator and then to evaporation ponds. At least now that's the alternative I'm thinking of. And then the product water, the purified water, would enter the potable water system at this point down here. All right. Let's go to the next slide. So this looks like a complicated slide in a way, but let me explain. Vertical scale is flow in MGD. Horizontal scale is years. And what I've shown here is the tertiary effluent flow coming from the treatment plants. And that would be after diversion to conventional reuse, which means that would be available for RO treatment, except for one thing. And is there anybody here from the Las Vegas Wash Coordination Committee? Yeah, Brenda, maybe? Or you go to the meetings?
Yeah, it's been a while.
Yeah, Las Vegas Wash Coordination meeting. They should have another meeting in another couple of months, I think. But anyway, that Las Vegas Wash Coordination Committee has, what's the word? Strongly requested that 70 mgd be left in Las Vegas Wash. Don't take all of the tertiary effluent out because that's the major flow into Las Vegas Wash. So Las Vegas Wash is an effluent-dominated stream, as EPA calls it. So there is a base flow. Base flow is the urban runoff, the seepage, and precipitation. That base flow averages around 30 mgd, or 32 or 33. So subtract from 70 means that we can allow about 32 or 33 mgd to go to the wash after we've taken our feed to the RO treatment system. But as we design and think and plan for the RO treatment capacity, we can only build so much at one time and then kind of follow and try to keep capacity above the blue line, which is the feed flow to RO treatment as a result of the tertiary effluent still going to the wash and then it's left over for RO treatment. Okay. I know that's a little complicated, but that's the way it has to be. You notice that I tried to make 25 into D, 75, 75, 80, 40, 30, 25, 20. And that's to keep up with what the demand would be and still not waste a lot of capacity. Okay, next. So issues to consider with direct potable water reuse is return flow credit, cost and public perception, as I just mentioned before. I'm going to go into cost right away because I want to explain return flow credits a little more in just a minute. And I had it listed first on that other list. But let's look at costs. Now here I'm going to have to, Carl, how much time do I have left?
About 20 minutes.
10 or 15 minutes?
20 minutes.
20 minutes, oh great. Okay, because this will take a little bit. I'm going to give you a little bit of engineering economics 101 here. Whenever you compare two projects, and they have costs, you always look at the capital costs and the annual O&M costs. Capital and the O&M, and apples and apples. You try to compare those costs. However, the capital costs of so many millions of dollars cannot be added to millions of dollars per year as an O&M or annual cost. So you have to annualize that capital cost. And there is a way to do that using what's called capital recovery factor. Chris, you're probably familiar with this. Capital recovery factor takes into account the interest on the money, like municipal bonds is around 6%. It takes into account the service life. In my case, design year 2050 from now, or from the year 2017 when we get started on the project, is about 32 or 33 years as a service life. So interest rate and service life will give you a capital recovery factor. But also before you can do that, you should do a present worth. And you're familiar with that, Chris. Present worth is studied and understood by even the senior year engineering students when they get into engineering economics. Present worth means if you have a project and you have part of the project that you don't need to spend money on yet because of various reasons, say it's 5 years off, then those 5 years you could have that money in a bank gaining interest, say at 6%. So that money at 6% applied to the capital cost would be the present worth of that project. So I did this present worth on the various, the treatment plant, the pipelines, the product water pipeline, the product water pump station. I did it also for the 300-mile pipeline, all the facets. They have pump stations and different size pipes and pressure regulating stations. Are some of you familiar with that project here? The direct potable water, the groundwater development project at SNWA? Okay, so there are those different portions of that project that I had to look at, not only the capital, the present worth of that capital, and then annualize that capital and add it all together so that I could have apples and apples, total annual costs against total annual costs. Okay, that said, let's go to the next. This is the capital cost of the groundwater development project, and I lumped it all together, capital cost at $4.15 billion. Now, I know that in the newspapers they talk about $15 billion project. Maybe you've heard about this, but it's actually around it was estimated some years back that about $3.6 billion, billion with a B, dollars. That's $3,600 billion. But that was like years back. Now, if you add cost of living or inflationary factor to that, you can get up to about 4.15. Is that what I have here? Yeah, which is $41.50 million. It's a capital cost, for the groundwater development project, the 300-mile pipeline. So then I did the present worth factor at 6% for all those portions of the project, added them up, divided by the actual capital, immediate capital cost against the present worth, and got a weighted average, so to speak, present worth factor. And that present worth factor is this 0.81. So you apply that to the 4150, and you have present worth of capital cost, $33.99 million. Now, capital recovery factor at 6% and 32-year service life is 0.0710. It's a complicated formula. I won't even show it to you. I don't have time. So the annualized capital cost, this times this equals this, $241 million a year as an annualized capital cost. Let's go to the next one. The annual cost, there's a lot of electrical costs associated with the groundwater development project. Mainly, the pumping from Boulder Basin to Las Vegas Valley. Glenn, where are you? Yeah, we talked about this. There's more electrical cost involved with this alternative as opposed to direct potable water reuse alternative, because there will be less water pumped from Lake Mead, from Boulder Basin. Keep in mind this figure here. Almost $100 million a year just to pump water from Lake Mead up to the River Mountains area, the River Mountains Water Treatment Facility area. And then I have listed all the other electric costs related to the groundwater project. There is a minus because they're going to have a generator station, and I made an estimate of about $15 million a year savings. So that's algebraically added. So I get 97.7 there as a total electrical cost. And when you add personnel, electrical equipment repair, and salinity damage in Las Vegas Valley at 35.7. Let me explain salinity damage. Bureau of Reclamation has already looked into salinity damage in Arizona, California, and Nevada. And they've come up with a magic figure of $134 per ton of salinity, or per ton of TDS. Or, Adrian, we know it as pounds per day, right? Well, you can actually go tons per year, and then we can relate dollars per ton and arrive at 35.7 as the salinity damage in Las Vegas Valley. There's actually a lot more salinity damage in Arizona and California, but I haven't listed it here because I've been told by some people from an engineering firm that I can't do that because you expect a check from California? No, I guess you can't do that. But I can do it for Las Vegas Valley because it's a direct salinity damage cost. So that's why I have it listed here, $35.7 million a year. That's the damage in the water heater replacements in residences, the damage in municipal treatment plants, and in other places, in plumbing, where high salinity scales the pipes and so forth. Also, you're drinking higher salinity water, which is, I can't put a number on it. Let's go to the next. Okay, now I'm on not the groundwater development project. I'm on direct potable water reuse alternative. We're going to look at the capital and then the annual cost. And we'll add the total annual cost, compare it with the other apples and apples with the pipeline. Okay, here's the total project capital cost that I have come up with, $3.9 billion for doing a direct potable water reuse, and it involves many, many conservative estimates of the RO treatment facilities, a brine concentrator facility, product water pump station, product water pipeline to connect, and an effluent interceptor near Las Vegas Wash that would intercept and collect the tertiary effluent from various treatment plants. You'd have to have that. However, that pipeline has already been designed by Clean Water Coalition in their scope project. They've already designed that effluent interceptor. So it's kind of an advantage for me. The other advantage is the present worth analysis. said, I went through and did the present worth and all the different sub-portions of the total project and arrived at a weighted present worth factor. And there it is, 0.6458 times 3941 is 2545. Same capital recovery factor as the other alternative, apples and apples. So I arrive at an annualized gap cost of 180. If you're keeping track of these bottom line costs, good. But don't worry, I'm going to show in the summary in just a minute. Here is the annual cost for the direct potable water development. I'm sorry. Let's go forward. Here's my annual cost for the direct potable water reuse. And you'll notice that pumping from Boulder Basin now is not 100 mg, 100 billion gallons, and $100 billion per year. It's 63.5. Why is it less? We're pumping less water from Boulder Basin up into the ground. However, we still have to account for pumping that water through the RO membranes, which is not at 250 psi as the old membranes used to do for brackish water, which is what we have. But it's now down to 150 psi with newly designed membranes. So that is a big benefit to me in my estimation. Also, there's a marginal cost of pumping through cartridge filters, $500 million per year, an additional amount, and I get a benefit of about $3 million a year with a pressure exchanger at the RO treatment. You understand that when you push water through an RO membrane, it's what's called cross-flow membrane. It's not plugged, not all the flow goes through the membrane. You get a cross-flow, and at the end you have the brine that's still connected to this pressure that you're applying. So you have all this free pressure. The product water is going someplace else. But the pressure that you have still remaining in the brine can now be routed through a pressure exchanger, and you can run it through the pump that's pumping into the RO system. So you gain a benefit there. And I've estimated conservatively at about $3 million a year. So the total electrical cost is $113. It's a little more than the other alternative. However, we make it up in just a minute. There's personnel, chemical equipment. And Dr. Batista, I thought Dr. Batista was going to be here today, but she's not. When she saw that, she said, wow, $32 million a year just for equipment repair. But she didn't, I had her type in membrane replacement, because a membrane is good for about 7 years, each membrane. So you're replacing membranes about once every 7 years. Depends how many membranes you have. And so I've calculated that in and reconciled all of that into a very conservative $32 million a year. And there's that solidity damage now is at about $11 million a year compared to, what was it, about 37 with the other alternative. Let's go to the next slide. And we have the summary. Groundwater development, direct potable water reuse, add the annualized capital, add the annual, for a total annual cost, total annual at 394 against 367. Those are the two magic numbers. Can you see them? Is it emblazoned in your mind? It's 394 against 367. And the difference is about $26 million a year. Is that $1 million per year? Yeah. $1 million per year divided by what you're comparing against, which is 394, is 6.7% difference between the direct potable water reuse alternative as opposed to the 300-mile pipeline alternative, in my estimation. I would welcome another engineer or another consulting engineering firm to look at my numbers and refine them and see if it comes out kind of close to what I have, I hope. Okay. Any questions so far? Let's go to the next slide. Return flow credits. We'll talk a little bit more about return flow credits. There's an interpretation that I see. First, from the state of Nevada perspective, it's a credit allowing added diversion of the Colorado River to our legal entitlement. Now, that's a big benefit for us to have that much return flow credit. So that's the way we see it here in Nevada. However, Bureau of Reclamation might see it as something that ultimately maximizes the flow in Colorado River. They're the water masters for Colorado River, Bureau of Reclamation. So they want to maximize flow available to everybody. So they see it as a little bit different perspective than the state of Nevada, as I see it. Okay. Also, down below here, can you see this down below? Traditional thinking perceives RO treatment as a low and a medium water recovery process. In other words, if you put 100 mgd in an RO membrane, the traditional thinking is that you get about 80%, maybe, well no, about 80% water recovery, meaning 20% is lost to brine. And if it was seawater, it's even worse because you only get about 50 to 55%. Yeah, and about 80 to 90% of packaged water at 2,000. The difference is because of the concentration of salinity, it's harder to push seawater through a membrane. But we have, Adrian, maybe you can help me here. Do you know what your TDS is coming into the plant or leaving the plant? Is it around 1,200?
Yeah, right around 12.
Right around 1,200. And you have a little bit higher than the other plants because you have some groundwater infiltration. Has high TDS down at the lower end of the wash. The other plants maybe be 1145, City of Las Vegas plant. Anyway, it's not 2,000. Oops. It's not 2,000. It's around 1,200 at the most right now. And in later years, it's going to increase. Why is that? Anybody have water softeners at their home? Yeah, I'm sure that many more of you do. But you realize that that brine goes into the wastewater collection system, to the sewer, and it's a high concentrated brine. I don't know what the concentration is. But it adds to the TDS that you receive at the wastewater treatment plants. And in your NIPDs, in your NPDES discharge permit, Adrian, you're fully aware of this, there is a goal of no more than 400 milligrams per liter TDS increase in your discharge compared to the water coming into the community. Okay? That's 400. It's not a mandate. It's not, if you violate, you're fine. But it's a goal. They want, EPA and NDEP wants you to try to get there. But what happens is it's always around 500 or 550 instead of 400. Why? Because at least 200 of that is from water softener brine discharge. The other is from normal soaps and urine and everything else that goes into wastewater treatment that adds to TDS. So, I'm telling you that the wastewater treatment plant tertiary effluent is going to gain from 1,200 maybe up to around 1,300 by the year 2040 or 2050, way off in the distance. Might be up to around 1,400 if they continue with the same water softener use that's happening right now. It's contributing around 200,000 pounds per day of TDS, by the way. Okay, so that said, we'll go to the next. Return flow. Yeah, however, as I'm saying, it's not that bad a situation with RO, with my direct potable water reuse. An RO system membrane array that contains a second stage RO, taking the brine from the first stage and putting it into a second stage, and then taking that brine into a brine concentrator. That total water recovery of that system is not 80% or 85% anymore. It is, what am I showing there? 99.85. In other words, what is it? 0.15% is lost and would have to go to an evaporation pond or some other disposal method. So it's only, how much, 5 minutes? 5 minutes. Okay. I'm almost through, so that's good. So it's a very low loss. So it does not affect return flow credits as much as some people think, because we could recover a lot from the RO system that I envision. Okay. So the only disadvantage is the relatively high unit capital cost. When I say unit, that's dollars per gallons fed to the brine concentrator, and the high unit O&M costs for the brine concentrator. But I already added those costs in those previous costs that I showed you, so I'm not going to go into it anymore of that. Therefore, the loss of water from the total system is extremely small. Yeah, I went ahead and used that 0.85, 99.85, which is about 60 or 70 gallons. It's like if I had my neighbor have a garden hose and I had my garden hose running at 10 GPM each, that's 20 GPM. So that's a small flow compared to our whole Las Vegas Valley water system. Okay. Public perception is the next issue. Costs, reverse osmosis, return flow credits, and public perception. Those are the three challenges that I mentioned before. So public perception. A history of public perception shows that with sufficient orientation and publication, public outreach, perhaps some public relations people going to Kiwanis lands, church, schools, to all these community groups and presenting what really can happen, like Orange County did with their system, that they gained their public acceptance. And they went ahead with their 70 MGD water reuse project. And I can show this also with other water reuse projects. Then eventually, the public can accept this indirect potable water reuse and direct potable water reuse. Now, you know the difference between indirect and direct is just an environmental barrier that is used after indirect potable water reuse. Like Orange County uses spreading basins in the crater basin, where Imperial Airway goes over. Yeah, where the water seeps into the ground, goes, and then it's pumped out. So it's an environmental barrier. In San Diego, they're going to be having indirect potable water reuse by using San Vicente Reservoir 15 miles away, and then it will go into their potable water system. So that, I don't believe public perception is a problem. I can show these case examples, but I don't have time to talk about all of them. I will talk for just a second about Big Springs, this going here, that's Big Springs, Texas. They're about to go online in another 2 weeks, maybe 3 weeks, with direct, if you read me right, direct, not indirect, direct potable water reuse. They'll be taking their treated through RO membranes, just like I discussed, and putting it into their potable water system. They'll be the first in the nation that I think is happening. Also, Cloudcroft, depending on where you see that purified water being added to their system. I think it's going to a tank which has the blend of their potable water system. So that's also direct potable water reuse. This is direct, this is indirect, 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 and indirect. So there's several systems using water reuse, treating wastewater. Let's go to the next. That was the first diagram I did. I really want to show you the next one, which is better. This is acceptance from 0 to 100% of either engineers who know about what water reuse really is. That's the dotted line, the dashed line. And then the solid line is the general public, as I see it. What their acceptance is for cooling tower makeup water, which everybody accepts that as no problem, way back in 1960. Oh, by the way, I've got 1950 to 2040 on the bottom. This is 0 to 100%. Landscape irrigation was a little tougher sell, but finally everybody went for it. And now we are looking at indirect potable water reuse, which, as I said, several systems in the United States, several systems around the world, environmental engineers have fully accepted this by the year 2012. And I see the general public with education accepting it here in another couple of years. However, direct potable water reuse is still another little hard sell that it needs public education, public orientation, public outreach programs. And I'm saying that by the year 2020, we'll have most of all the engineers online and general public by 2025. Okay. Conclusions. Okay, Carl? Okay. The background information shows that the potable water resources for Las Vegas Valley are limited. We know about that. Increased demand is going to overwhelm by the year 19 or 20. Okay? Groundwater development project, which is the 300-mile pipeline, sponsored by SNWA, is more costly than direct potable water reuse project in terms of money costs and environmental costs, which I would love to talk about environmental costs, but I'm not an expert in that. I was hoping Dr. Deacon was going to be here. I talked to him a couple of days ago, but he couldn't make it. He was going to make some comments. But definitely there's big environmental costs. Issues of cost, return flow credits, and product perception need not be negative issues. This is my summary. My recommendation is that the alternative, direct potable water reuse, be planned, designed, and constructed as soon as we can. Okay, questions? Lights? Yes?
What's the risk posed from some of the non-traditionally treated for chemical constituents like nicotine, pharmaceutical residuals, that kind of thing out of wastewater with a direct return?
Yeah, what's the risk in the direct potable water reuse scheme?
Yeah, so, what's the effectiveness of an RO unit in removing those constituents?
Okay,
how much will
there's
pass?
been studies of this. I'm not an expert on that either, but the reverse osmosis membrane pore size is such that it can remove molecules down to about 100 molecular weight. They call that the molecular cutoff. Most of the things you just mentioned, endocrine disruptors, caffeine, and all these pharmaceutical products are above 100 molecular weight. So what I'm saying is, as far as I know, reverse osmosis membranes are going to remove maybe 95 to 99% of all of that. But even if they don't remove 1% or 5%, how does that compare with the water we're drinking now? Do you know that? Because there's plenty in there.
I think the Orange County plant using advanced oxidation.
Yeah, oh yes.
And that removes some of those constituents.
And we would be using that same thing.
The plant in Green Springs does that. It's microfiltration, and you have the RO as water, what it's proposing, and then you have a UV peroxide process at the back end to take care of, add more disinfection and add some protection on the side also. But some of those compounds, they will go through the RO. Risk, I think no one knows the answer for that. That's a big question out there. We know that there are environmental risks. We can have one. There are environmental risks in
Oh,
SNWA,
damn,
and their
yeah.
research here, they found that on fish in Lake Mead, so, but I don't think there are, we know yet the risks for us.
Did you hear the question?
So from a lot of the studies that are out there right now, in terms of the public health risk, they're very low if there's any at all. But on the other side, environmental risks are a lot higher if you have any constructors going out to Lake Mead, for example. So it's actually better for us to drink it ourselves rather than put it out there because the environmental risks are greater. So the concentrations that we see even in like secondary effluent based on the studies that are out there right now show that there's really no public health impacts from the trace organics that are in the pharmaceuticals and things like that. So even before reverse osmosis and advanced oxidation, we're pretty much okay in terms of public health.
Good, Dan, thank you. And Chris. Yeah. Besides what we've just said, I would propose that we put this purified water, product water from the RO, ahead of the River Mountains wastewater treatment plant, which has ozonation. Is that right?
Yeah.
And which would also do a job. So I think we're fairly good. Any other questions?
Have you pitched
Yeah,
it
good,
to
Brenda.
SNWA?
Huh?
Have you pitched this to SNWA?
I was hoping somebody would ask that, and then I was hoping not. Because no, I have not pitched this to SNWA. I think that the word is going to get out here soon, and I'm going to have to pitch it to somebody from SNWA, whether it's Pat Mulroy or her staff or both, I don't know.
Well, one interesting note I was going to add is that I think the situation's even more dire than what you showed because some of the newer predictions for the lake levels indicate that we're going to hit 1050 by 2016, very soon.
Yeah, so.
Yeah, this is with the recent Bureau of Reclamation decision to cut flow from Lake Powell by 10%, namely 0.75 million acre feet, which is 10% of 7.5 million acre feet. It's going to reduce from 8.23, correct me if I'm wrong, Dan, 8.23 down to 7.48 million acre feet per year coming from Glen Canyon Dam. So that we will feel that in Lake Mead, of course, and it will start descending even faster, as you said, Brenda, than what we had thought before. Right now, I checked the newspaper this morning, and it showed back on the last page. Do you ever check this? The last page of weather, and it gives the temperatures, the normal, the actual, and then it gives the elevation of Lake Mead. It was 1106.89 in the morning newspaper this morning. 1106.89. However, if some of you tune in to on the internet Bureau of Reclamation page, that is their lower basin operations sheet, and it shows for September for reservoir level, I've red circled April 2015 as reaching 2075, which is the trigger point for the first shortage level. Yeah.
So with that in mind then, what about the implementation time? Is there's definitely a lag in implementation of the groundwater program. What's the length of time to implement this?
Yeah, that's a good question. How much time will it take to get the direct potable water reuse system going?
Yes.
Boy, that's tough to say. First, there would have to be some pilot plant work. I'm sure that, Chris, you would know about something like that.
I don't know if there is any plan
On doing
from
this.
the authorities.
But just
They've been doing pilot studies at the McCarty facility with microfiltration membranes and RO and ozone also. They've done that, but it's not out there as a
No.
something that is
no, it wasn't intended for micro.
Yeah, it was intended to improve the water quality in the lake, not to bring it back.
Yeah. Okay, thanks, Chris.
But results are there.
Yeah. So to answer your question more fully, first there would have to be some pilot plant work. That's what I'm asking. Thank you. Then some conceptual design. the normal, like what you're asking, what years would these happen? I don't know. But I'm estimating that maybe all of that could happen, the design and start construction, maybe by the year 2017, or at the latest 2018, to have a 25 MGD plant, RO plant, online.
And so the general technology for the membranes, et cetera, is in place.
Oh, yes.
So the construction of a new, just regular wastewater treatment, a nice wastewater plant like we have in the valley today, from start to finish is like how many years?
Oh, to construct the plant?
I mean, so I'm just saying as a point of comparison, one of our existing plants, for comparison, how many years did that take from construction?
Sometimes
It's difficult to say if we're talking about just the tertiary treatment, in 5 to 8 years, by the time you have, it depends on the agency. Also, some agencies it takes 1 year just to pay the project.
Right.
And,
But those are times.
but if you're talking about a whole plant full, well, then it could be more.
Yeah.
What was the Southwest plant? How long did that take?
We were just talking about that. I think once, we're talking about Henderson's Southwest Water Reclamation Facility. Like once we went out and did everything and awarded to the contractor, it was 2.5 to 3 years.
To construct.
Actual construction.
Yeah.
And that's an 8 MGD capacity advanced wastewater.
What are
From the
10
design,
8.
8.
from the design going, from the design.
Design's a little bit harder because it went all the way back to site location and all that was in 2005. So
Those are things that take time. It may not take as much money, but it takes a lot of time, which is resolving, just to resolve a permit or something like this, because they don't have legislation in place, will take years. So it's a major deal to implement. As the pipeline is. And as the pipeline is, that's what it's called.
That's going to be important.
Exactly.
It also depends on urgency and location. Like in Texas, for example, in Big Springs, they did it really quick. And then if you had to do something like that in California, who knows how long it would take. Because they're setting like 2016 as their deadline for coming up with their own potable criteria. So they're 3 years out just to come with criteria, let alone design. And then in Texas, you're building the plant right away because it's so urgent.
So on a fast track, you can do that.
Yeah, Australia is the other example where they spent billions of dollars because they needed it so quickly.
Yeah. So that can happen. But I get your point. I think your point is that my estimates are a little bit too optimistic.
No, I actually didn't have a point. Other than that, I actually wondered if it was an advantage over the groundwater project because I see the legal hurdles and all holding that up.
Yeah.
But this discussion was illuminating to me because clearly there are somewhat similar hurdles under a usual process for this. So you can't claim it as an advantage.
Yeah.
Clearly, anyway.
What is your name and where are you from?
I'm not going to tell you. I'm Jenny Chapman. I work here at DRI. I'm a hydrogeologist, not an engineer. So that's why I didn't have an idea of those concepts.
Okay. Thank you.
Well, you talk about public perception not being a big deal at this point. I always thought that public perception was the most challenging.
Yeah. I
Thing
agree.
to deal now because engineering is there, regulations are not there, but actually to educate people and to make them accept the toilet to tap concept,
Yeah.
it's hard.
I know. I agree. In Orange County, maybe Dan, you might know, I think it was close to almost $1 million spent on public relations just to get the good word out to everybody. They even had the bishop. Do you remember that?
I don't know. That's before my time. Before I was
Reclaimed water.
You were related to San Diego.
Yeah, I'm more San Diego. I was still in high school and all that
Okay,
stuff.
what have they do? What have they done in San Diego?
San Diego, they built a 1 million gallon per day demonstration project, and over the course of, I don't know if it's been a year or 2 years, they bring in public tours almost on a daily basis. Because going back even further, San Diego was the toilet to tap place where it all fell apart in the past.
Yeah.
And so they were really careful when they it got to a point where they needed to implement that project again. And then this time around, they were really careful. They built that demonstration project. They really tried to get out to the public and show them that it works really well and the water quality is really good. And so they now, like, fast forward 5 years from the toilet to tap issue, it's a completely different story. The public's accepting of it, and they're even considering direct potable reuse now in San Diego. That's how far they've come.
Oh, they are considering direct?
Yeah. So like you mentioned, they're going to put that water in the reservoir. And it's like a 22-mile pipeline.
Oh, 22.
Yeah, so instead of all the energy costs associated with that, they
Yeah.
want to consider just getting rid of that pipeline and just using that water right in San Diego. So instead of sending it away and then bringing it back again, just use it right there.
Will some of it go to Alvarado?
I don't know.
Oh, okay. I used to work for the city of San Diego, so I'm familiar with what you're saying.
I was just up at the Water Reuse Conference in Denver
Oh,
and saw a
good.
presentation on the Orange County plant.
Good.
And they actually saying that they're getting people who weren't in that first cycle of information that are coming through and touring the plant and seeing all the technology and going through, wow, that's really neat. So at the end of this, you put the water in the ground? Why don't you just put it into the pipe?
Yeah.
So, the suggestions are coming from the people
From them,
who, but they have something to look and see and not just the drawings there.
Oh, you mean that comment was from just a general public?
From people taking tours.
After
And
they had some education?
They quoted some number, I remember doing the math in my head, it was over a tour a day. It was over 365 tours in a year.
Wow.
Last year. It was wow. I was trying to figure is that 7 days a week? Is it 5 days a week? They do a lot of tours.
There was another recent public perception study where they came up with the same conclusion that they would talk to the public and show them all these different schemes that are out there. And then when it came to an Orange County type system where there's reverse osmosis, that was the comment that always came up. Well, why don't we just drink it? Why do you put it back into the ground? And that was a consistent comment that came up. So that's how far we've come.
Yeah, that's great.
That's it.
Yeah. So I think public
It
perception,
seems that we are making progress on that, right?
yeah, we've made a lot of progress.
There's certain places in the country.
Yeah, Carl.
Yeah.
Oh, okay. Any other questions about public perception or costs or the return flow credits?
Well,
Yeah.
I'm not as familiar with the Northern Pipeline project. You did the annualized cost per year of the two projects, but how do the flows compare?
Oh, yeah, good point. Good point. I want to say my, I shouldn't say my. The direct potable water reuse alternative is being thought up by some crazy guy. That flow would take, as I explained, all the tertiary effluent that would be available, except for the tertiary effluent that has to go to the Las Vegas Wash, maybe by 3032. So horizon year 2050, design horizon year, is somewhere around 390 MGD going to reverse osmosis. On the pipeline, you know how much MGD that's good for? Out of those valleys that I showed you, now if they take Snake Valley, that makes a big difference. But Snake Valley is very controversial right now. That might not happen. But Delamar Valley, Dry Valley, and King Valley will produce, they have water rights, according to the state engineer, for 114,000 acre feet per year, divided by 1120.22. That's the conversion. And you get 102 MGD, 102 against 390. So if I put a dollar value on this per gallon, the dollar, but I don't think you can do that exactly. Yeah, it's almost reconcilable.
Going back or going further with that, how much water is available up there? When would they predict that the groundwater would be depleted?
Oh, I don't know. It could happen. I don't know if it's an if or when.
Well, I don't-
According to the state engineer, that shouldn't happen.
Yeah, it's not gonna be completed.
Yeah, it's legislated and there will be monitoring taking place and so forth. But it's a good question because it's a system that's not really fully understood at this point.
They're expecting it to be coming
Yeah,
out of
that's
a perennial
right.
yield, so they're not going to recharge it, then nothing comes out, so
So,
Even that number is.
theoretically,
Yeah.
that's the idea.
Right.
yeah. Oh, good, you're a hydrogeologist. there is a connection between one valley to another?
In the system they're in, I believe so.
There's
but-
transmissibility, I mean?
But that's not exactly the point he was asking.
No. But it's all related, in my mind. Do we know how much the groundwater level might be descend after so many years?
Depends on whose consultant you ask.
I don't know what that is. That might be a
There's
subject.
no. We don't know.
Yeah.
We're never gonna know unless.
Yeah.
I think
Okay.
the state engineer in that case has been taking the approach that it's, the only way you'll know is by monitoring it as it's happening. And when you make the argument that when you start to see the impacts, it's too late. They're
Yeah.
going to continue on into the future, even if you reduce nothing. So
Yeah.
a lot of rest.
Right.
This has been a really great discussion. I really want to thank Walter for coming over and giving this presentation.
Sure.
Thank you all for participating.
Thank you for being here. Okay. I have some literature up here in case anybody's interested on direct potable water reuse and the acceptability